2 projects. In this video, we are going to explain about the project title, A Predictive Model to Detect Cervical Diseases Using Convolutional Neural Network Algorithms and Digital Colposcopy Images. Introduction. Cervical cancer originates in the cervix and is often linked to HPV, human papilloma virus. Prevention involves measures like vaccination against HPV, routine screenings for early detection, and various treatments based on the cancer stage and severity. Cervical diseases, especially cervical cancer, are a significant concern worldwide due to their high mortality rates and prevalence. They pose a substantial challenge for healthcare professionals and researchers, contributing significantly to global mortality statistics. Existing solutions for detecting cervical diseases have limitations, including equipment constraints and the types of tests used. These limitations hinder accurate early detection, impacting the ability to identify cervical diseases in their initial stages. The project introduces a novel approach employing deep learning algorithms and digital colposcopy images to overcome the limitations of existing detection methods. By utilizing advanced technology, this predictive model aims to identify various classes and stages of cervical diseases more accurately. Objective. The project aims to create a predictive model using deep learning algorithms and digital colposcopy images to accurately identify various classes and stages of cervical diseases, prominently focusing on detecting cervical cancer. This endeavor is driven by the need to overcome the limitations of existing detection methods, particularly in accurately diagnosing early stages of cervical diseases due to equipment constraints and the sensitivity of medical detection tests. To revolutionize cervical cancer screening, the project concentrates on harnessing the power of deep learning algorithms. This approach seeks to introduce faster and more sensitive methods, presenting an opportunity for the medical sector to enhance early stage diagnosis of cervical diseases, thereby significantly impacting healthcare outcomes. Throughout the project, 4 rounds of rigorous experiments are conducted. These evaluations meticulously assesses the model's performance, emphasizing metrics such as accuracy, precision, recall, and F1 score. These metrics serve as critical indicators of the model's capability to precisely classify diseases and minimize the occurrence of false diagnosis. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This initial step involves importing various Python libraries essential for the project, such as TensorFlow, Keras, Pandas, and NumPy. TensorFlow and Keras are critical for building and training deep learning models, while Pandas and NumPy facilitate data manipulation and handling. Exploring the dataset. Cervical cancer. Analysts meticulously examine the cervical cancer dataset's attributes, including its structure, distribution, and statistical characteristics. This exploration phase helps understand the dataset's composition, variations, and patterns, aiding in informed data pre-processing and feature selection decisions. Image processing using image data generator. Rescaling the image. Adjusting pixel values within a defined range to standardize and enhance model convergence during training. Shear transformation. Applying controlled deformations or tilts to images, adding diversity to the dataset to improve model robustness. Zooming the image. Altering the image magnification level, introducing variations for better model adaptation to diverse image sizes. Horizontal flip. Creating mirror images horizontally, augmenting the dataset to improve model generalization and performance. Reshaping the image. This module ensures consistency in image dimensions required by the model architecture. Operations include resizing images to a uniform size and converting color format if necessary. Feature extraction. Reading the image involves loading images from the dataset into memory, preparing them for further processing. Resizing the image. Standardizing image dimensions to match model requirements, ensuring uniformity in data. Convert the color. Adjusting color formats, example converting RGB to grayscale for image compatibility with the model. Appending the image and labels. This step connects images in the dataset with their respective disease labels. Each image is linked to its specific classification, forming pairs that the model can learn from during training. Conversion to NumPy value. Images are transformed into arrays of numerical values to enable computational operations. Pixels within images are converted into matrices or arrays, facilitating mathematical manipulation for the model's understanding. Label encoding. Categorical disease labels like benign or malignant are converted into numerical representations. This transformation assigns unique numerical identifiers to different disease classes, allowing the model to interpret and learn from these classifications. Building the model. Here, the architecture of the convolutional neural network CNN is created. This includes defining layers, connections, and configurations within the neural network to facilitate learning patterns from images. Training the model. The model is trained using the label dataset to learn the relationship between images and the corresponding disease labels. Through iterative adjustments of parameters, the model minimizes prediction errors. Flash framework with SQLite for sign up and sign in. This involves setting up a web application using Flash, a Python web framework, and incorporating an SQLite database for user authentication. Users can register and log in before using the system. User upload an image for analysis. Users can upload their digital colposcopy images via the web interface. This function enables users' engagement by allowing contributions to the disease prediction system. The given input is pre-processed. Before prediction, the uploaded image undergoes necessary processing to align with the model's requirements. Tasks like resizing or color conversions are performed to prepare the image for analysis. The trained model is used for predicting the result. Utilizes the learned patterns from the trained CNN to predict the disease or classification of the pre-processed user-uploaded image. This step generates predictions or probabilities related to the detected disease. Final outcome is displayed through front end. The prediction result, such as the identified disease or classification, are displayed to the users through the web interface. This provides an intuitive and interactive presentation of the predicted outcome. Algorithms used. To implement this project, we have utilized the following algorithms. The first algorithm is EfficientNet B0. EfficientNet B0 is a convolutional neural network architecture known for its efficiency and high accuracy. It employs a compound scaling method that balances model depth, width, and resolution to achieve better performance with fewer parameters. EfficientNet B0 is commonly used for image classification tasks due to its effectiveness in extracting features from images while maintaining computational efficiency. VGG16. VGG16 is a deep convolutional neural network composed of 16 layers. It is characterized by its simple architecture consisting of multiple convolutional layers followed by max pooling layers and fully connected layers. VGG16 is utilized for image recognition and classification tasks due to its deep architecture and ability to capture intricate features in images. ResNet 50. ResNet 50 is a residual neural network architecture with 50 layers, featuring skip connections that enable the network to learn residual functions. This design helps prevent vanishing gradients during training, allowing for the training of deeper networks. ResNet 50 is widely used in various computer vision tasks, including image classification and object detection, owing its capability to handle deeper networks more effectively. VGG19. Similar to VGG16, VGG19 is a deeper variant with 19 layers. It follows a similar architecture of stacked convolutional layers, pooling layers, and fully connected layers, making it more complex and capable of capturing finer image features. VGG19 is suitable for image classification tasks where a more intricate feature extraction process is required. CNET, that is CNN modified. CENet is a customized convolutional neural network modified specifically for the project's objectives. This indicates a specialized CNN architecture with enhancements to suit the requirements of disease detection from colposcopy images. CENet, being a custom CNN, is designed and optimized for specific tasks, potentially offering improved performance for the given dataset and classification objectives. DenseNet. DenseNet, densely connected convolutional networks, is a neural network architecture where each layer is connected to every other layer in a feed-forward fashion. It promotes feature reuse and encourages gradients to propagate more effectively during training. DenseNet is effective in learning intricate patterns and features from images, making it suitable for various computer vision tasks, including disease classification from medical images. Logistic regression. Logistic regression is a statistical method used for binary classification. It models the probability of a binary outcome based on input features by applying a logistic function to a linear combination of the predictors. In the context, logistic regression is used for simpler analysis or baseline comparison for disease classification tasks. SVM, Support Vector Machine. SVM is a supervised machine learning algorithm used for both classification and regression tasks. It works by finding the optimal hyperplane that best separates data points of different classes. SVMs are effective for classification tasks and can handle high dimensional data well, making them suitable for image based disease classification. Random forest. Random forest is an ensemble learning method that builds multiple decision trees and merges the predictions to improve accuracy and reduce overfitting. Random forest is suitable for classification tasks, offering robust performance and handling complex relationships in data, potentially beneficial for disease classification. These algorithms play a crucial role in leveraging machine learning and deep learning techniques to analyze digital colposcopy images and detect cervical diseases, providing a diverse set of tools for effective disease classification. As an extension, we applied an ensemble method that combines the predictions of multiple individual models to produce a more robust and accurate final prediction. Comparison graphs. Comparison graphs offer a visual breakdown of how a model performs across essential evaluation metrics. Models are compared with the parameters accuracy, precision, recall, and FN score. This is the accuracy comparison graph. Here on the x-axis we have accuracy score and on the y-axis we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positive and true negative, to the total number of instances. This is the precision comparison graph. Here on the x-axis we have precision score and on the y-axis we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis we have recall score and on the y-axis we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis we have FN score and on the y-axis we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. The algorithm which is performing best in all the performance metric will be used for prediction. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are model files which contain algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. So here I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register. But I have already registered, so click on sign in. So here we need to enter the username and the password which we have registered, and then click on sign in. We have logged in successfully. So here we need to upload the image to predict the type of cervical cancer. So click on choose file. Select the image, click on open. Now click on upload button. This is the uploaded image and it is predicted as the patient is diagnosis has type 2. Let us upload some more images. Click on choose file. Select the image, click on open, click on upload button. This is the uploaded image and the prediction is the patient is diagnosis with type 3. Let us upload one more image. This is the uploaded image and the patient is diagnosed as type 1. In this way, just by uploading the image, we can predict the type of cervical cancer. That is whether it is type 1, type 2 or type 3. Now click on sign out button here. The conclusion of the project is the project's predictive model employing deep learning algorithms and digital colposcopy images demonstrates significant potential in effectively identifying various types and stages of cervical diseases, prominently including cervical cancer. By analyzing these images, the model shows promising accuracy in detecting and categorizing diseases accurately. The primary aim of the project is to facilitate early stage identification of cervical diseases, a critical factor in improving treatment outcomes. The developed model effectively fulfills this objective by rapidly and sensitively screening digital colposcopy images. Its ability to detect diseases at early stages contributes significantly to timely intervention and treatment. By providing a reliable and efficient tool for early disease detection, particularly in the context of cervical diseases, the project makes a substantial contribution to the medical sector. The availability of such a model for early diagnosis potentially aids in reducing the mortality rate associated with cervical cancer. Timely detection enables prompt medical intervention, increasing the likelihood of successful treatment and improved patient outcomes.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.